Hello class. In this lesson we're going to look at radioactive decay. We're going to be a couple lessons in before we really start breaking that down. We need to get some background knowledge taken care of first. And we need to distinguish between stability in the nucleus and stability with chemical reactions. So atoms have a couple different traits. They can be stable with their nucleus, and so that's stable, unstable, and that's a nuclear thing. And then they can also be reactive or inert, which I have also called stable or unstable. And this one is really only dependent on the valence electrons. So if something is going to react chemically, it's because it does not have a full octet. And so these elements right here are the only inert elements. Everything else is reactive, and that's because of their valence electrons. Remember, this has everything in column 1 has 1 valence electron, everything in column 2 has 2 valence electrons. We'll learn about this group eventually, but for now we skip over it. And so 3 valence electrons. Essentially what happens here is electrons fill in underneath, and so most things in here have 1, 2, or 3 valence electrons. 3 for here, 4, 5, 6, 7, 8. And remember, the octet rule says that when the outer level is full, that is, has 8 valence electrons, the atoms are stable. That is, they no longer react. They're inert. So chemical reactions, we're concerned about valence electrons. But with nuclear reactions, we're considering the nucleus. We don't care what the electron configuration is. We care about what's going on inside the nucleus. And there is no simple rule for this like there is for valence electrons. These are determined experimentally, so we can't tell just by looking at something whether it's stable or unstable. So this is lithium 1, 2, 3, 4, 5, 6, 7. Lithium 7 is stable. That means the nucleus doesn't change over time. It's going to remain like that. Whereas lithium, we've got 1, 2, 3, 4, 5, 6, 7, 8. Lithium 8, this is unstable. It decays. Okay? It's going to be radioactive. So when we're talking about nuclear stability, we're talking about whether or not it's radioactive, whether it's going to change into a different element through some kind of nuclear process. So there's two things that we really have to pay attention to when we're talking about the nucleus, and that's the strong nuclear force. Remember, the strong nuclear force only acts when protons are about a proton apart or less. So if this space is fairly small, less than a proton, the strong nuclear force really wants to hold them together. But if they're fairly spread apart, then the electric force that repels them really wants them to go apart. So when we have a large nucleus like this, we can see that some of the protons are within a proton of each other, so they're very strongly combined. But like this proton here and this proton here, they're not strongly held together by the strong nuclear force, so the force that they primarily feel is the electric force pushing them apart. And then the neutrons in there are also causing some changes and some either stabilizing or destabilizing things. So that's the other thing we have to look at when we are deciding whether or not something is stable or not. And so the number of neutrons has an effect. So not only the size of the nucleus, a larger nucleus tends to be unstable, but if the wrong number of neutrons are there. So if their neutrons are less than their protons, that tends to be unstable. Not always, but usually. Or if we have way more neutrons than protons, that also tends to be unstable. And so we'll take these on a case-by-case basis, and you can actually look up in tables the stable isotopes of an element. Okay. So with an unstable nucleus, radioactive decay occurs. This is just the spontaneous emission of particles and usually, or energy and usually particles. And so what we see here is this polonium nucleus underwent decay, and by that we mean it changed into something smaller and also emitted something. And that something that it emits is always energy and usually some type of particle. Now that particle might be a neutron, might be a proton. In this case it's what's called an alpha particle, which is 2 protons and 2 neutrons. Might be an electron, might be a positron. We haven't talked about positrons before. A positron is the size of an electron but has a positive charge. Okay. So decay, it becomes slightly smaller. It does not mean it disappears or goes away. It just changes into something different if it gives away a particle or releases some mass as energy in the case of gamma decay, which we'll look at later. Now, the easiest way to talk about these things is to use isotope notation. So this says molybdenum 96, and that right there is the mass number, but we can also talk about this with isotope notation. And when we do that, we write the mass number and the atomic number. So 96, and then I go find the element on the periodic table, and it's element number 42. Okay, and so this is mass number up here, and this is atomic number down here. Now, we do it this way, even though this is redundant, right, because 42 and molybdenum are the same thing. We do it this way because we're going to be looking at decay reactions, and there's a rule where we're always going to have the same number of particles at the beginning and at the end. They might not be in the same atoms anymore, but this way we can quickly see, oh, how many protons did I start with? How many protons do I end with? Okay, and so on the lecture tutorial, we are supposed to look at these things and write them in their isotope notation. So lithium is element Li. It says lithium 7, so it's got a mass number of 7. And lithium, if we find it on the periodic table, is the third element, so it's got an atomic number 3. This says atomic number 5, which means I'm going to look at the periodic table. The fifth element is boron, so B. Mass number 11, that goes up here, and my atomic number goes down here. And then number of neutrons is 10, the number of electrons is 9. Remember, atoms are neutral because they have the same number of protons as electrons. So this tells me my atomic number is 9, and element number 9 is fluorine. So this is fluorine, and it's got 10 neutrons. 10 plus 9, protons plus neutrons, is 19. So there is the isotope notation for fluorine 19.